I would like to thank everyone who attend this webinar. So today I'll present quantum key distribution. So I'll try to make it as an introduction for someone who is new to the field. So I will start by pointing out at the current cryptographic systems issues, the key distributions issues that we have right now. And then I will go through an introduction for the quantum computing because we have some who are new to the field to know about quantum computing and how it's done. So then I will go through 4 major quantum key distribution protocols. Then I'll present some of the actual implementations of these of this technology. Then the challenges, and the future directions. Then I will conclude. So I'll start by this, which is as we use internet for everything in our lives, for studying, for shopping, for communicating, for everything, almost everything in our life, we use internet. But what we want is a secure communication. So we want our messages to be secure. So the obvious solution, which is encryption. So encryption, we have been using encryption for several years to encrypt our information. So, and there are 2 main types of encryption systems. The first one, which is symmetric crypto systems. In the symmetric crypto systems, a single key is used by the sender and the receiver. As you can see, just a single key is used by both of them. So Alice will encrypt this message using this and send it to Bob. Then Bob will decrypt the message. But the real issue is how Alice and Bob agree about this key. How Bob knows about this key. How Alice communicate this key to Bob. So these crypto systems are good, but the issue is with the keys themselves. So another type of these crypto systems, which is asymmetric crypto system. In this type, it's convenient. It solves the issue of key exchange. How it solves it? We use 2 different keys. So this is the first one, the public key and the private key. So these 2 keys belong to Bob. So anyone who wants to send a message to Bob, so the message should be encrypted using the public key, and because the public key is known for everyone. So, and only Bob knows about the private key. He will decrypt this message and knows what's in it. So by doing so, we solve the problem of key exchange. As before, we don't know how to communicate these keys, but here we know how. But the other problem is this secure? This always will be the question forever. Is this secure? Actually, it was assumed to be secure. It's secure. It was secure, but not anymore. Why? Because most of these public key cryptography systems are based on a mathematical problem that's believed it's difficult. So the computing complexity is so high that an attacker cannot break. So just to show an example here. So we have here this figure that shows the key length. So as we increase the key length, and here the computing time. So if we choose, this is the key length for this encryption, to encrypt this data. So the receiver who requires this time to decrypt this data, which is, as you can see, that the time of encryption and decryption with the key is linear. It increases by increasing the key and also the data maybe. So, but if an attacker trying to decrypt the data without the key, so the time required to do so increases dramatically, as you can see in here. So this is what's believed about about all cryptography systems, and specifically for this public key cryptography. So unfortunately, by the advent of quantum computer, so these public key cryptography systems, it's believed they are broken. Why? Because quantum computer can do calculations, which is much more faster than a classical one, which means the possibility of breaking these algorithms is there, it's guaranteed. So, and there are two main algorithms that have been proposed in quantum cryptography, which is Grover algorithm. This Grover, it attacks symmetric cryptography. But as we can see here, in symmetric cryptography, we have several algorithms, but the security of these algorithms, they are not broken yet, but the security level decreases or cuts by half. So as you can see here, this is the security level before, and this is the security level now. So it means by applying such algorithms, we are minimizing the search space to the half, then we do the attack. But for these algorithms, because they rely on factorization and all these things, and Shor's algorithm for in this prospect, it can break these if we have a powerful quantum computer. So it's believed like if we have RSA algorithm with this key length 2048, so using our classical computers, it's believed like we need billions of years to break it, but we can see later how. So let's assume the same data, the same key, but we take the most powerful classical computer in the world, which can break this algorithm in this point. So this time, but this is abstract time, we didn't know it might be in years. So, but the problem in here is this: the increase is exponential. So if I increase here the key, if I choose the key here, so maybe this algorithm or this computer cannot break it, or maybe break it after 10 million years or something like this. So our classical computers, the computation in breaking such algorithms increases exponentially. So and the thing is, the sad news is, we cannot make any faster classical computers. So we started from the past, building our computers, and we did great, yes, but we almost reached our limit. So we cannot make, like we are talking about a single CPU, we cannot make it any faster due to several limitations. If we can have a look at this is CPU like Intel, and as you can, this is it, and Intel backs about 100 million transistors in each millimeter. So can you imagine the space and the amount of transistors in this area? It's immense, and we cannot increase more because the space, the cost, and the heat management. So it's almost, we are reaching our limits in creating such powerful machines. And what we are doing right now, what they are doing is adding cores, doing parallel, and all these things. So, but a quantum computer, a quantum computer can break these algorithms in a linear time, not exponential, linear. So we say, if it can break it here, and this one can break it here. But if I increase the key by this, so this quantum computer can break it by this. So the gap is not that big. But here, maybe it is in million years. So the gap is so huge because it's exponential, while here is linear. So for these reasons, so we, as we can see here, this is the predictions for the building the quantum computers. And as we can see here, if we have this quantum computer that holds this number of qubits, we break RSA with this much of key length. So what we have right now, like in 2018, we accomplished like 72 by Google, and the race is going on in building a bigger and a better quantum computer. So the thing that's really scary, and is that intelligence agencies now, they are storing data. So if we can't break this data, what we can do, we can store it for the future. So it's believed that intelligence agencies storing traffic of specific agencies, companies, political figures, and international secret, maybe conversations. We store them now, and once the quantum computer is there, we decrypt them, and we will know what was going on. So for this reason, we need to move on to a new technology. So what makes quantum computing superior is this. So in classical, we can make it in a simple way, large objects. We deal with large objects. Dealing with large objects, it means you can know anything about it. You can, like dealing with a car, we can know the location, the momentum, the velocity at any time. I can measure the location while it's moving. I can measure the speed of the car while it's moving. So I don't have to stop the car to do any of these. But in working with quantum, we are working with tiny or massless objects. These tiny or massless objects that we cannot measure unless we disturb them. So what we can do only, we predict. We predict this electron will be in this position, like by like 30% probability, or like 50% it will be here, or 50% it will be here. Just probability. We don't know for sure. And if we want to know, we need to intervene and to disturb this electron to know where it is, what's its location and its momentum or something like this. So this is something that keeps them secret. We have information and nobody can intervene with it. And if he does, the state will be disturbed. So one of the main things that you will see everywhere, which is the wave-particle duality in the quantum world, which is quantum objects behave like a wave function, which is like a wave, a sound wave or a water wave. If we are not measuring, if we are not watching, but once we are watching how they behave particles. So even though the same exact experiments repeated, only if there is a measurement device in here who is looking, or here looking at the particles, they start to behave differently. Which this phenomenon is amazing. Why? Because if an attacker is watching the, so the data will behave differently than if no one was there. So just to introduce what's called qubit. In classical world, we have bit, which is called either 0 or 1. But in quantum world, we have, or quantum computing, we have qubits, which is a quantum bit that holds 0 and 1 at the same time. If we can have a look at this. So like here, we have 0, only 0, it's up, only 0. Here, only 1, it's down. So this is only classical. But in the quantum world, we can put the qubit in a state that holds both of the states. So like here, so here is 0. So here is 0, here is 1. But if the qubit state is in the other axis, which is x, which is orthogonal to z, the qubit will be in a superposition state. And superposition means it holds all the states. It means 0 is there and 1 is there as well at the same time, and their existence depends on probability only. So just to give you an introduction about the notations, we use this bracket notations, which is like, this is kit, it's called kit, which represents a qubit in the 0 state. So we said the qubit could be 0 or 1. This is the vector that represents this qubit. And this value represents the existence of the state 0, and this represents the existence of the state 1. So in here, because it's 0, so this is 1, 0. It means the qubit is 0. But here 0, 1, which means it's 1 because the qubit is 1. But the qubit could be in a superposition, as we said, which means it's 0 and 1 at the same time. But we like put a symbol like plus or a minus to represent this qubit. So I hope I'm trying to go fast because there are so much materials. So I hope you understand. And if you don't, just hold the slide number and I can go back. So a superposition is a mixed state. So just by simply, if we just look at this, let's see, we have 4 different signals. Each one has different frequency. And when we sum them up, we end up with having this state, which is mixed state. We call it superposition. Why? Because it holds all the states all together at the same time. So, so let's assume we have this state, which holds 0 and 1. And we have here, we call it the state amplitude, which is alpha and beta, which represents like the probability of having 0 and 1 in there. So let's say we have this state and we want to find, is the 0 exist in this state or not? So what we will do, we do inner products. Inner product is just factors multiplications. This is the factor of, this is the state psi, the factor of the amplitude, which is alpha and beta. And we multiply it by the 0 factor. We know it, which is 1, 0. We just multiply and we end up with having alpha squared, which is, this one represents the probability of finding 0 in this state. And doing the same, we find beta squared, which is the probability of finding 1 in this state as well. And as we are talking about probabilities, the summation of these 2 probabilities should be 1. So when we do measurement, we destroy the wave. So we have it in here, wave, then it transforms to a particle. The same thing when we do measurement in here. So the photon behaves like a wave. Once we do this measurement, or we put a filter in here, so the photon start to behave like a particle, not wave anymore. So we can put our qubits in different axes, not only in the 0 and 1. We have x-axis and y-axis. I can go back here if anyone have questions to save time. So what we have in here, so similar to classical computing, we have gates and something like this. So the same thing here, we have, we can call these gates or operators. So we have X operator. So let's go through them. We have identity operator, which is, this is the identity matrix. If you multiply identity with any qubit, the state of the qubit stay the same. But if you apply bit flip operator, which is the X, so what it does is this. So we started by qubit 1, and if you apply this operator or this gate, the state of the qubit will be flipped from 1 to 0 and vice versa. Similarly, if you apply Z operator, which is phase flip, which applies on the qubits in the x-axis, not in the z-axis. So if the qubit was plus, it will transform to a minus and vice versa. And most importantly is the Hadamard gate or Hadamard operator. The beauty about this Hadamard operator is it's the matrix or the operator that creates the superposition. We say here like we have this is pure 0, pure 1, but here it is a superposition. Superposition, it means what? It holds 0 and 1 at the same time. So how we do that? By simply applying Hadamard gate to a qubit. So we have a qubit, we apply this Hadamard gate or Hadamard operator, and by multiplying this matrix, the qubit will be transferred from the 0 state to plus. What does this mean? It means like this. So we have our qubit was in here. Once we apply this Hadamard gate to it, so this qubit will be transformed into this, into plus. And if you apply Hadamard again to the plus, it will return it back to 0 state, which means Hadamard operator can transform between two bases. from the Z base to the X and vice versa. So, and we use this to create the superposition in quantum computing. And also another interesting gate that is used everywhere, which is the controlled knot. The controlled knot is like this. So it's not here we have not. Here we have not. If you apply to 1, you get, oh, sorry. If you apply to 1, to transform to 0. But here it's similar, but controlled. What does this mean? It means we apply not to Y, but only if X equal 1. So if X equals 0, the Y stay the same. But if X equal 1, the Y, like 1 becomes 0, and 0 becomes 1, and 1 becomes 0. So controlled not. It's not, but controlled by X. So what makes, so based on this thing, what makes it superior is because quantum computer can store so much information in one space. Like here in classical, you either store 0 or 1, but in quantum you store 0 and 1 at the same time. So we need 2 to the power n classical bits to encode the same amount of information that n qubits can do. And also the computation in classical computing. So let's say we have these 16 possibilities of data. So in classical, you need to check them one by one, but in quantum, you can check them all at once at one time by just designing the circuit. So we have another interesting property, which is the entanglement. The entanglement is when we have not single qubit, but 2 or more, we have them, they are linked to each other. Like this qubit is linked to this qubit. So how they link in this way, like if one of them is 0, the other one should be 0. If this one 1, the other one should be 1. So let's say we have these entangled particles, one of them in US and the other in China or something like this. So if you measure this, you find it 1. So without even looking at this, it should be 1 because they are entangled equally in here. So we can have 2 possibilities. We entangle them equally. It means if this 0, this should be 0. If this 1, this should be 1. So measuring 1 tells you about the other and even decide the destiny of the other. Also in here, if we entangle them opposite, it means if you measure the first one, you find it 0. It means the other one should be 1. If you find it 1, the other one should be 0. But I mean, this or this should be known from the beginning. So finally, we arrive to quantum key distribution because we need all that information to understand what's how these things works. So quantum key distribution is secured by the laws of quantum physics. And we have several protocols that have been used for quantum key distributions. I'll go through these 4 just quickly to give you an idea and how they work and how they are secure. So I'll start by pointing out at this phenomenon that we all know, but we don't know it's used in quantum world. So sunlight is unpolarized. It means like photons are oscillating in every directions, and we can have a light that only oscillates in vertically. It means the photons or things just oscillates in this way, and also we can have lights which oscillates on the only in the Z like horizontally. So this concept is used in the sunglasses that we are using. What sunglasses is doing, they block this light because this light is just a reflection from the surfaces. So it blocks this light. How it blocks it? It uses like filters like this that only allow this or this to pass while this is blocked. So let's look at this. So let's assume we have this light. This is the source of light, which gives us light which is polarized vertically. And we have filter here. This filter is also vertically. So because the light is vertical, the filter is vertical. So all the light will get through. So all the light will pass. But if we have the light, again, the light is vertical, but this is diagonal. this way. So because it's diagonal, half of the light will pass, not all of it. So it means like 50% of the light will pass and 50% will be blocked. But if we have this, which is vertical light, but the filter is horizontal, in this way, no light will pass. Why? Because they are orthogonal to each other. So the light is oscillating in this way, while the filter is in this way. So this light cannot escape this filter. So, and it will be blocked and nothing will be passed. So why can't we use this as a way of communication? So like I will use this filter. So we have the same light. We have this, I use this filter and this filter. If I want you to receive one, I will apply this filter. So, and you will receive one. And if I apply this, you will receive 0. So no light, it means 0. So this as a way of communication is utilized in this protocol to exchange secret bits. So what Alice and Bob is doing is this. So Alice apply, so like if we say horizontal and vertical, this is the filter. So we say like this is horizontal, vertical, but we can apply another operator, which filter, which is diagonal. We can apply this. And what we say about this in here, so this is diagonal, this is horizontal, this is vertical, and this is diagonal. So only half of the light will pass. So because the filters are different, so half of the light will pass. So if Alice sends a photon polarized in this way, and Bob does the measurement in the same filter, which is this one. So he is looking for the one. Is there one? Let's say up one. If it's like this one, see, this is one. And if it is horizontal, 0. So Alice will apply this filter, which means I'm sending you 1. And if Bob applies the same filter, he will also look for the 1. If a light pass, it's 1. If it doesn't pass, it means it's 0, and both of them will get the same value. But what if Bob applies another filter? So Alice applies this filter, but Bob applies this filter. So only half of the light will pass. So if he applies this filter, half the light will pass, or this filter, half the light will pass. So it means they are only 50%. They have only 50% of what they send. So Alice sent data, only 50% of them received by Bob, and the other get blocked. So they use this concept of blocking to detect if there is an attacker. Here is the overview about this protocol. So Alice choose what filter to apply, either cross or diagonal, and based on the filter, it decides the information. Let's have a look on this. So Bob in here chose diagonal, and I mean Alice sent this. Let's start from here. So Alice sent this. She chooses diagonal, and Bob, when Bob measures, he measures as well in the diagonal. So which means diagonal. So this bit we accept it. Here he used like vertical, and this used the cross filter again. So we accept it. But in here, so like, let me just choose the one that are different. Yeah, this is different. This is different. This is different. Yeah, like here. So Alice applies this filter, while Bob applies the diagonal. So because we applied different filters, so we don't consider this bit. This bit will not be considered, and this bit will not be considered as well, because he applies diagonal, I applied cross, so we discard it. Here cross, diagonal. So these, the ones that are applies different filters, we ignore them, and we use them to detect if there is an attacker in here. So to save time, I might go back to it if anyone have a question about it. So another protocol, which is 6-state protocol. it applies the same concept, but it adds another dimension. It works in X, Y, and Z at the same time, not the diagonal, but actual axis. So the other one, which is a beautiful one, it uses entanglement. When we say entanglement, it means we have two particles that are generated. These two particles are generated by this source entangled, and this source sends these two particles, send one send it to Alice, and the other one will be sent to Bob. So once Alice measures her particle and Bob measures his particle, they should receive the same exact information, And this protocols, there are so many protocols that utilize entanglement based, because we can generate a pair and we send it to everyone and we measure, we get the same data. But what if there is an attacker in the middle? We can detect it using what's called Bell inequality. So just let me show you in here. So once it's received, Alice may measure an A1, A3, and A2. These are three possibilities of measuring. Bob will measure either in B2, B1, or B3. So three possibilities here, three possibilities here. But how they generate the key? They generate the key based on those that we match. So if I measure in A1 and you measured in B1, so we accept this as a bit. This is good. So if I measure in A3 and you measure in B3, so again we accept this. Other than that, we just use them and apply what's called Bell inequality or CHS game. So by applying this, we take those pairs that doesn't match. Those that match, we use them to generate the key, which are these. But what about the others? The others, we use them to test if there is an attacker. How we test if there is an attacker? We just apply this is the equation to compute it. And if the value is less than 2, it means there is an attacker. And if the value is between 2 and 2 square root of 2, it means the pair is still entangled. And we can define here a threshold to accept or abort the protocol. So another interesting protocol, do I still have time? Another interesting protocol, which is the entanglement swapping. So I might go back to it. So entanglement swapping, I will just go through it. So we have this pair and this pair, they are entangled. So let's say this is Alice and this is Bob. So what Alice will do, will send this particle to Bob, and what Bob will do, he will measure these two. By measuring these two, this one and this one, they will become entangled while they have never met each other before, and which is a really great feature that have been used in several quantum key distributions. So this is how it's secure, because it detects an Eavesdropper. And is this just a science fiction? No, it's not, because we have several companies that have it's already there. Devices, you can just buy this and plug it into your server and use it. And as we can see here, in 2004, the world's first bank transfer using quantum key distribution. It is the most mature quantum technology, because it doesn't require huge number of qubits or something. 2, 3 qubits is enough to do the exchange and generate the key. So they have done it through satellites, and they have done it internationally between different countries, and they done it underwater as well to test it. And the future of this technology could be to build what's called quantum internet. Just imagine if we have internet like this, you send your data and nobody can change this data while it's transferring. So it's secure by nature. So there are several challenges for quantum key distributions, which are, there is a gap between theory and practice. Still, there is a gap. And we have difficulties in integrating these systems with our existing networks. And some of the companies just try to solve it by you plug this to your server, and they build like integration surfaces between the key distribution and the actual. But yeah, we still need more. And also we have only point to point. We need point to multi-point as well. And we have the main and problem, which is long distance quantum key distributions. As we cannot use routers or repeaters in the middle, because if a router take the qubits and copy it, it will be destroyed. So we cannot use repeaters in the middle or routers to do so. So this is the main challenges. And as a conclusion, so quantum key distribution, it's a must to use it in current days, because we need to exchange secret or secure keys. And it's a must not only to use quantum key distribution, but to use quantum safe or quantum based cryptography. And the good thing about KKD is this: it's unlike quantum computing. In quantum computing, we are waiting to develop a most powerful one, but here it's already there and it's working, tested, and there are so many products that are already in the market. So thank you.